Thank you, Dimitris. If you allow me to be a few minutes off schedule, because ASHRAE and conferences is one part of our life. In Serbia, we have a national union of mechanical and electrical engineers. One part of this union is our national HVAC&I society, which organizes a large congress and exhibition in December Dimitris was speaking of. And on behalf of our president, also ASHRAE member, but Professor Bratislav Blagojevic, most of you know, I am honored to give a recognition of our National Union of Mechanical and Electrical Engineers to two of our very dear colleagues and I can say friends, to Dr. Konstantinos Balaras for exceptional contributions to the advancement of engineering and technology in Smedz, Serbia. Mr. Balaras and Dimitris are elected to distinguished member of our national society, and it is my pleasure to give you this prize. I must say that this, how to say, recognition is, how to say, it's a very small circle of people who are recognized by our national society.
Thank you.
And it is a pleasure of being here and having you in Belgrade. Dimitris.
Thank you very much. Great. Αυτό ειλικρινά δεν ήταν προγραμματισμένο, είναι μεγάλη αίτηση και μεγάλη τιμή. Ευχαριστούμε πάρα πολύ.
We thank you very much.
Thank you.
Okay, so we are on track. This is a part of the research we have started a few months ago with my colleagues who are given here. One of them is a professor in architecture and he's dealing with passive design strategies for building renovation, especially for public buildings, let's say schools, and this is the one of the issues we have started working on recently. What is the most important, as we heard from the previous presentation, a lot of energy is consumed in buildings, but also due to population rise and further urbanization, this increase in building energy usage will probably continue. Also, if we go from the building perspective to a district or a city perspective, the share of percentages in energy use and in emissions is larger if we include transport or other sectors relating to buildings. This is the idea we found that sometime we are at the end of this period that until 2030 urban area will triple within world. And if we do not have proper urban planning, even at the building scale, we cannot solve every problem or problems that may happen in the future, like we saw, so we can have a severe environmental impact in pollution, in ecosystem degradation, etc. There is a strong tendency to develop both methodologies and methods not to treat the building on a small scale, but rather to zoom out and to put it in some urban context while doing some analysis on the building itself. There are research who deal with input data uncertainty, and this research shows that if you zoom out from a building level to a, for example, district level, of the district which building is part of, there is a strong tendency of reducing relative errors if you zoom out, even for one particular building. Why is that? Because with this approach, you can include everything that is surrounding the building and impacting the thermal balance you are calculating or predicting on a yearly level. Also, with these new methods and methodologies, you can also include for urban heat island effect. We in Serbia don't have this strong feeling, except maybe some parts of Belgrade, what it's actually about. But I remember a couple of years ago, I was in Thessaloniki in maybe early July, and it was I was feeling much warmer in some parts of the city than the actual thermometer said, and it was my first experience of real, how to say, heat island effect in a how to say, city square. And also at that time, I know that colleagues from Aristotle University of Thessaloniki were dealing with some cool payments in order to reduce the heat island effect. So probably it was, how to say, a fact that citizens experience. Also, all these microclimate changes impact building energy performance. Warmer temperatures can decrease heating needs on one side, but can increase cooling needs, unfortunately, on the other side. And also some other parts like shading, like structures that block the direct sunlight can lower cooling demands but increase heating demands. Here are the roughly percentages given in the literature. So as you can see, it can warmer temperatures can decrease heating by as much as nearly 20%, but can increase cooling needs up to 40%. And on the other hand, if you have surrounding structures of a building, we can increase heating needs by as much as 30% and reduce cooling needs by as much as almost 50%. Why is this important? So our idea is to do a district level analysis, even if we are dealing with a particular building. This is one part of the problem. The other part of the problem is if, as an architect, you try to refurbish one building, you still try to, how to say, put it in a wider perspective, not to be an isolated entity, but to be a part of the block or a district which is already a part of. So we need integrated building models. Like I said, there are some methodologies and methods developing how to look at this type of problem, to have a building and to analyze everything which is inside the building, but also to include everything around it. There are some modeling challenges. If you use some simulation software for building performance simulation, there are some limitations when a number of zones starts to increase, you also have some runtime issues that simulation can last long. It can, how to say, it can mislead you to focus on some minor details which are not that important on a bigger scale. And this is why we introduced model simplification. You will see on the case studies shown that with model simplification we can group several building zones into one zone to do analysis on this zone, but still maintaining the correctness or to capture the interaction between this zone and its environment, neighboring environment. So, how we got to this idea? A couple of years ago, we were modeling one big settlement near our faculty in Niš. It's more than 30,000 square meters in 20 buildings. And since we had design projects for each building, we started developing the models individually. And from the previous experience, we noticed, because we had indoor measurements, etc., from previous experience, we knew that if you have a good replication of building geometry, of building materials used, of the building systems installed, then in the off-season, when the systems are not running, if you put, how to say, the real weather data the building was exposed to, the measurements of the inside parameters and the simulated values within the same zones would pretty much match. So kind of pre-building energy model calibration. But we noticed something interesting, that on the sides of the building, which did not have anything to block the sunlight, the direct sunlight, we had a good match. But on the sides of the building where shadows may be casted in some part of the day, we didn't have this, how to say, a good match. So we integrated all individual buildings into one model. So, for example, 20 buildings in one model. If someone is interested, I can give a reference for this building and the paper. And when we included these all buildings which can cast shadows on itself, we find a good match between simulated and measured values. And this was okay. It was not in our focus that time, etc. Then, a few years ago, my colleague Dusan Anđelović, who is an architect, was dealing with passive design strategies for school buildings. And for some buildings in city of Niš, he found that they are underachieving. So we kind of looked into more detail and found out that, for example, for these two school buildings, one on the left side is actually a primary school my kids are going to. It's how to say, it was built in an open environment with a lot of greenery on the side, etc. There are now no surrounding buildings. And on the other side, we have another elementary school, pretty much both of them are rather old, which was already part of some urban area back then. We translated the models, and before the simulations started, we wanted to see how this building energy performance matched with real data provided by our district heating company. And we saw that there was a lot of mismatch. So basically, we modeled the buildings, we got the projects from the National Archive, we entered the capacities of the heating equipment, we figured out the schedules of the building use, of the system use, of the set points, etc., and still did not got a pretty good match. And then the thing with the large settlement popped up, so we cannot forget about these green areas. It was planted 50, 60 years ago. Now these are big trees with large canopies, blocking the sun. Also some greenery was stuck in between these pieces of the building. These are some, how to say, descriptions of the both building types. And after creating simulation models, we did basically two simulations. One was we treated the building like island, and for the case study building 1, we found that this is energy need for heating, specific energy need for heating without surrounding structures. And when we implemented surrounding structures like trees, some barracks for serving food for kids, etc., when we implemented this in the model, we got this parameter. On the other hand, for building number 2, it was still an increase, but not that much, because if you remember, building two was already put in the urban area, and let's say this is a cardinalist direction. A lot of this glazing is on the east side, so this shading impact was not that great for the second school. These are the monthly values of energy consumption for heating for both case studies without and with surrounding structures. We see a huge discrepancy between the two cases, especially in April and October. The reason why April and October are in red, because in Serbia, I don't know what is the case in Greece, in Thessaloniki, for the fact I know you don't have a district heating developed. In Niš, all, let's say, primary schools, or most of the primary schools and public buildings are connected to district heating system. And we have a local regulation that says that heating season starts on 15th of October and ends on 15th of April. And basically, from my experience with district heating, October and April are the months where you can make huge mistakes. So if you hit, you can make a mistake. If you don't hit, you can also make a mistake. So April and October are the months which are most problematic. So we try to put the simulation to run it as the district heating operates the school building, both of them. But in fact, you must know that, for example, every maybe 3rd or 4th October, there is actually a need to heat in October or in first half of the year, just because this is our local law, let's say, that you must heat after 15 October until 15 of April, no matter what. So this is the basically the same schools, but we put like some shading surfaces to represent some trees, to represent some adjacent small food kiosks for etc., to represent surrounding buildings in this context. And on average, we see an increase of 8.3%. If we include surrounding structures for this case study building 1, in period actually, which is real heating season from November until end of March, is only 6.7, and for the second school, which was already well planned and incorporated into an existing settlement back in the 50s or 60s, this increase was much smaller, which means that the architect initially designed the building by incorporating these surrounding structures, and this is why we should include them in our energy performance. So, like I said, this is only a start of our research. We do not have a large project team, and our intention was to let's say, to find primary schools in Niš which must include, to give a recommendation that for which primary school you must include the building surrounding while developing some energy refurbishment, whether it's a facade, it's a window replacement, heating system replacement, etc. So hopefully next year we will have some real results to see the whole picture in the city of Niš. Thank you. If you have any questions, I will be ready to answer. Thank you.
Thank you.